All right. Well, I hope I don't let you down. Um, it's interesting. The way that we find this area is, well, through not through any sophisticated calculus method yet. It's still a calculus method, but it's not. You're going to feel like, oh, that's all we do. But I'm kind of taking you through the steps, and trust me, the steps help you to eventually understand the calculus method a little more. So we're going to end up actually first just approximating the area. And don't let that word approximation kind of have a bad ring to it. Again, this is all part of the steps in the process, but we're going to use what's known as the rectangle approximation method. I'm not making this up. This would be like the same way it would be taught in any calculus course. It's actually abbreviated RAM. A little cheesy, but it is the way it's abbreviated. Basically, we're going to take this area and we're going to divide it up into some rectangles. I know it's not rectangular. It's obviously curved, but we're still going to divide it up into some rectangles. Now, in order to do this, you're going to find out that we need something known as a subinterval, or how many subintervals. This is like a decision that either the book would make, or the question on the test would be. It would say, let's use a certain amount of subintervals. So we'll use 3. Just letting you know that we could have used 4, 5, 6, 10. We could have divided into any number of subintervals. Now, a subinterval is really just a name for the number of rectangles. So what that really means is we're now going to end up with 3 rectangles from 0 to 6. And you can do a little bit of just kind of common sense math. The technical math that you'll need for some harder problems would be that the length of the subinterval is always going to be, of course, the total length divided by the number of subintervals. Again, kind of common sense math. You probably could already tell that the length of the subinterval is going to be 2. What that means is that we're going to get a rectangle from 0 to 2, from 2 to 4, and from 4 to 6. So we're basically going to divide this into 3 rectangles, 3 subintervals. Okay, there will be some problems you guys do down the road where you're going to actually sort of question, wait a minute, how do I find the length? So you find the length by dividing it by basically the change in x over the number of subintervals. Now, in order to draw these rectangles, you're going to find out that there's 3 ways, there's sort of 3 sides that we can pick in each subinterval. And the first way, or the first side, is if we do this to the right. We actually call it right RAM, or right-hand rectangle approximation method. So it's RRAM, but again, that's because we're going to do it to the right. What are we going to do to the right? I need to show you. It's always that first one that you kind of see, oh, okay. I'm actually going to start in the last subinterval, just because we have more space over here. And so from 4 to 6, my eyes are going to kind of go to the right side. I did draw a little line here, but my eyes go to the right. And of course, that takes me to number 6, which I then will go up and encounter the curve. So I'll go up and I'll encounter the curve on the right side. And I'm going to go ahead now and draw the rest of the rectangle so that you can see that our first rectangle would be that one. And you should be looking at it and saying, it seems like it's like outside of the curve. Well, yeah, it is. But it's all right. It's part of the process. Now, let's do another one. If I go to the right side of the next subinterval from 2 to 4, if I go to the right side, I encounter the number 4. I go up to the curve. And that vertice helps me to draw my second rectangle. And maybe you feel like you can draw the one that would start this region. It would be the one that if I go encounter 2 on the right side, I meet the curve, and we have that rectangle. Now, I did draw these backwards. I kind of started at 4, 6. I say I drew them backwards because typically this first one from 0 to 2, that would be called R1 because it's the first rectangle. This one would be called R2, and typically this one would be called R3 for either region 1, 2, 3 or rectangle 1, 2, 3. Okay, now, yes, the rectangles I just drew are too big, but they are technically the right rams. They are the rectangles that go with the right side. And so what we want to do is we want to find the area of each one of these. Of course, the reason we want to find the area of each one of them is so we can add them all together. As you think a little bit about the area, I hope that you realize that the width of each one of these rectangles has already been determined to be 2. And I hope you realize that the height of each of these rectangles is actually a point on the graph. Now, it's important, okay? Realize that I'm just using a parabola, but because it's a parabola, that means that every y value is going to just be the x value squared. So I get a y value of 4, I get a y value of 16, and get a y value of 36. Make sure you understand that those numbers would be the height of each one of those rectangles. So my first rectangle is a 2 by 4. My next rectangle is a 2 by 16. And of course, the last one's 2 by 36. So we have the width and the height of each rectangle, some pretty basic math, which is actually why this is a nice method. It's pretty basic math because obviously we're just doing length times width. Don't shoot down this rectangle method, even though the first one we look at sometimes seems like there's got to be something better. Oh, there is actually something better, but right now this is kind of what we got. All right, so what do we end up here? 8, 32, 72, 40, 72. I think that's 112. Okay, and that would be in this case, we would call it the right ram, which remember is the right-hand rectangle approximation method. We don't make a big deal about units squared. I'm just going to be honest. I am not going to write that all the time. I will the first time and today because technically it is the area. Okay, now I know every one of you would say, yeah, but it's like too big. Yeah, it's too big, but it's something. You know, a few moments ago we didn't have anything. So at least we know that the area is going to be less than 112. And it kind of allows us to bring up or to think about another way to draw rectangles. As I mentioned, let me just say it again, it allows us to think about or bring up another way to draw rectangles. Now I'm going to lead this conversation a little bit. I hope you're thinking about some other ways, but right now I'm going to lead you into another way. So what I'm doing here is I'm still using 3 subintervals. If you're getting yourself prepped, everything we're doing here is good stuff. It's still 3 subintervals from 0 to 2, 2 to 4, and 4 to 6. But there's another way to draw the rectangles. There's another way. Again, since I'm leading the conversation, I'm going to say that we could draw them to the left. We actually call it the L ram. We could draw it to the left. Now, this is important. I do sometimes see kids, it's like, oh, wait, how do you do this? Well, I'm going to start in the last interval again. It's sometimes easier to start there for the first problem. Watch how I do this. I actually go to the left of my interval. So I kind of start at 6, but I go to the left. At the number 4, at the left side, I go up and meet the curve. Basically, I go up and meet the curve so that I can create my rectangle. Well, as you can see, a left-hand rectangle. See how we did that? We went over to number 2, went up and met the function. Now the first one here, which is why we usually don't start with this one. If I go over to the left and try to go up, there's nowhere to go. So of course that rectangle really isn't a rectangle, or to say another way, it has no area. You should start to see some patterns here, simply one of them being that the y values, even the y value of 0, but the y values have a direct connection to the area. As we get into deeper problems, you'll be going back to that thought. So we got 3 regions, 3 rectangles, whatever you like to call the letter R. They're still all 2-bys. Do you see how some of the numbers are shared in the 2 rams? Specifically, the y value of 16 shared in both of them. 4 is actually shared in both. It's kind of like we just have a different starting y value, or for this problem over here, a different ending y value. All right, so we have 0 plus 8 plus 32, 40. Pretty big span, but you shouldn't be super surprised that this area is coming out less. Remember I said don't totally write off rectangles. You should be looking at what we did so far and feel like, wait a minute, I could come up with a pretty good average, right? You come up with a pretty good average right now. Does that mean that the real answer, is the average? Not necessarily. I'm just saying that would be a better answer. So we got these 2 answers, we could average them. But since I'm kind of leading the conversation, I'm going to lead us to one other way to draw the rectangles. Now, it's still going to use 3 subintervals. So I am kind of curious if you're thinking, I know that I haven't really let you share yet, but can you think of another way that we could draw these rectangles that I'll say could be better? We drew it to the right, we drew it to the left. Can you think of another way that we could draw them that would be better? We drew it to the left, we drew it to the right. What about if we draw it in the middle? What do you mean, it in the middle? Well, it's this whole thing about where you meet the function. If I go to the middle of this subinterval, I kind of create a new x value. If I go to the middle and I go up and meet the function, then my rectangle has a little bit extra and a little bit missing. It seems like my rectangle is a little more balanced. Now we call this the M-ram for middle rectangle approximation method. The M-ram. I'm just going to pause because you should feel like that. I hope you feel like that it's helpful to think about the rest of this. Maybe you can even figure out the whole answer. But can you draw some more rectangles? And can you think about doing it with M-ram? Think about some of the things you're doing for every problem. For every problem, you're using y values. Those y values are actually the dimensions or part of the dimensions of each rectangle. Make sure you're still using the overall width. The overall width was decided way back in the beginning to be 2. Each rectangle has a width of 2. Okay, so we're still using 2 bys. Okay, so we get a rectangle that's, I got an area of 2, 18, and 50. Okay, now notice I haven't said like which one of these is right, because the honest truth is that none of them are, quote, right. Okay, they're all estimations. Some of them might be better than the others, like this last one. But we can still use all 3 of these estimations to come up with probably the best answer, at least the best approximate answer. So maybe you did it. It's easy to do. You can just average all these numbers, obviously add them up and divide by 3. It turns out to be a number that's different than all the numbers up here. But if I find the average, 112, 40, and 70, that average comes out to be 74. 74. Now remember that's the area under that parabola, or technically the approximate area under the parabola. I'm going to throw out that same question again. Can you think of another way to draw the rectangles? Can you think of another way to draw the rectangles? You should have been looking at each one of these rectangles and kind of saying, they're really boxy. You know, like I get all this extra space. I have all this unaccounted for space. It's kind of balanced space, but it's still boxy. Okay, but what if you were less boxy? What if you had smaller rectangles? What if you had a smaller subinterval? Okay, obviously a smaller subinterval is going to make more rectangles. If you have more rectangles, won't they fit in there a little bit better? Okay, well, the answer is definitely yes. Calculus, or the theory of calculus, eventually says that you want to have an infinite amount of rectangles. Are you tracking with me? If I draw an infinite amount of rectangles under here, well, then it's going to be perfect. Okay, and eventually that's where this is headed. Okay, but of course I'm not going to make you draw that, but we'll do that kind of theoretically. All right, that'll be a good place though to kind of pick up tomorrow. We need to discuss a little bit more about this RAM method